All right, welcome to lesson 3.1. Well, chapter 3, we are going to be looking at systems of equations. In this lesson specifically, we are going to solve systems of equations by graphing. If you look at the objective, that is the first half of the objective. The second half is analyzing the number of solutions to a system without graphing. Because basically what we'll see as this lesson unfolds is that there are three different scenarios that can happen when you solve a system. And based on one of those three scenarios, it'll tell you how many solutions you can possibly have. A couple definitions before we get started. A system of equations is a set of two or more equations that use the same variables. So two equations that both have x and y, for instance. A linear system is where each equation in the system is a line. That's what we're looking at here. So a system of equations could be anything. We're specifically looking at two lines. A solution of a system is a set of all the values that make the variables in all equations true. So it's the value of x and y that would make, in what we're going to look at first, the two equations that we're looking at both true. All right, so solve each system by graphing. How do you do that? Well, you're going to graph both lines, and then we can take a look at the result. Two ways to do it. Since it's in standard form, you could graph the intercepts. However, with the first equation here, if I solve for the x-intercept, it would be a fraction. So I'm going to just solve for y and get it in slope-intercept form. So I'm going to subtract 2x from both sides and get y equals negative 2x plus 5. All right, so that means the y-intercept is at 5. And the slope is negative 2, so down 2 and right 1. All right, and then we'll draw our line through that. Just going to pick a different color for this line. So I'm going to add x to both sides. And I get y is equal to x plus 2, meaning y-intercept's at 2, and the slope's 1. So that's up 1, right 1. The solution is where they intersect, the ordered pair where they intersect, because that's the only ordered pair that works for both lines, because that's where the two lines touch. So the solution to this would be the ordered pair 1, 3. All right. Check your solution in both equations. So if we substitute 1 in for x, 3 in for y, 2 times 1 is 2, plus 3 is 5. 1 in for x here makes it negative 1, 3 in for y here, negative 1 plus 3 is 2, so they both check out. All right, we'll do the same thing with this one. I'm going to convert this equation slope-intercept by subtracting x from both sides. And you get 3y is equal to negative x plus 2. Divide both sides by 3, and you get y is equal to negative 1/3 x plus 2/3. When I go to graph that, not ideal that you have a y-intercept that's not an integer, but you can deal with it. So 2/3 we'll say is a little closer to, well, not there at all. It's a little closer to 1 than it is to 2, not negative 1. So we'll say it's right about here, right? And then the slope is negative 1/3. So that means I go down 1 and right 3. And I go down 1 and right 3. So we'll draw our line through that. Okay. Let's choose a different color for my other line. This one I'm going to subtract 3x from both sides. And I get 3y is equal to negative 3x minus 6. Divide both sides by 3. And I get y is equal to negative x minus 2. So that is a y-intercept at negative 2 and a slope of negative 1. So that line looks like it goes through like that. And it looks like it's intersecting right here at 1, 2, 3, 4, so negative 4, and then up 2, so 2. And again, you can check your solution. So substitute negative 4 in for x, you get negative 4. Substitute 2 in for y, 3 times 2 is 6. Negative 4 plus 6 is 2. Negative 4 in for x here makes that negative 12. 2 in for y here makes that 6. Negative 12 plus 6 is negative 6. So this solution checked out for both. Right, now getting to the second part of the objective, you can classify a system by the number of solutions. What we just looked at for those two examples is this situation here. They're intersecting lines. Where they intersect is the one solution, and that's considered an independent system. Notice how the lines are blue and red. It's purple here because the blue and red line are on top of each other. So there's actually two lines here. That's considered coinciding lines. You could also call that overlapping lines. I think that's usually the phrase that I use. There's no unique solution here, which also is another way of saying infinite solutions. Because every point on that line is a solution to both equations. That's also considered a dependent system. Parallel lines, where the two equations have the same slope, have no solution. Right? That's also considered an inconsistent system. So depending on what the question asks you, if it's asking you for the solution, you'll either give an ordered pair, or you'll say infinite solutions, or you'll say no solution. If the question's asking you for or to classify the system, the classification is going to be either independent, dependent, or inconsistent. So this question says to classify the system without graphing. Well, if I go back to these pictures, what you can notice is the first thing that would be a piece of information that you'd want to know in order to try to group a system into one of these three categories is the slope. If the slope is different, it's going to be an independent system. The lines are going to intersect at one place somewhere. If the slopes are the same, then it's either dependent or inconsistent. And then it's just a matter of, is the entire equation the same? Then they're overlapping. If the slope is the same, but the y-intercept is different, then they're parallel lines, and that means they're inconsistent. So what we need to do is be able to compare their slopes. So I'm going to take both equations and get them in slope-intercept form. So I'm going to subtract 3x from both sides here. And you end up with y is equal to negative 3x plus 5. Here I'm going to subtract 15x from both sides, and I get 5y is equal to negative 15x plus 2. Then I'm going to divide by 5, and I get y is equal to negative 3x plus 2/5. They have the same slope, but different y-intercepts. That means they would be parallel lines, so this would be an inconsistent system. If the question was asking for the solution is no solution. If I look at part B, the first equation's in slope-intercept form, so I don't need to do anything. The second one, I'm going to add 4x to both sides. And I get 2y is equal to 4x plus 6, divide everything by 2, and you get y is equal to 2x plus 3. Turns out they are the same equation, so this is what's considered a dependent system. Let's look at the last two. Here I'm going to subtract x from both sides, and I get the opposite of y is equal to negative x plus 5. Divide everything by negative 1, and I get y is equal to x plus minus 5. Here I subtract 3, and I get y is equal to 2x minus 3. They have different slopes, so this is an independent system. They're going to intersect somewhere. So there's going to be one solution there. So if this was, again, asking you for a solution, you would need to find that ordered pair. First equation is done for you. Add 6x to both sides, so you get 2y is equal to x plus 4. Divide everything by 2, and you get y is equal to 3x plus 2. Turns out it's the same exact equation. So again, this is a dependent system. If it was asking you for the solution would be infinite solutions. All right, make sure that you do the exit ticket. That's going to count in your classwork section of your gradebook, and then the practice will be available tomorrow.